This is section 26 of the SAT Math Manual. Section 26 of the SAT Math Manual deals with right triangle trigonometry. Some students do find trigonometry to be a little bit intimidating. Obviously, it is one of the more advanced concepts that will appear on this test, but fortunately, the trig that is tested on the SAT is very basic trig. The stuff that most students get introduced to in 9th or even 8th grade, not really the stuff that you will tend to deal with in pre-calculus. The law of sines and cosines, the trigonometric identities, although the Pythagorean identity may be tested occasionally on this test. That more advanced stuff you will not see on the SAT. You may see that material on the ACT, but you will not see it on the SAT. Most of the trig on this test, again, is fairly basic. It's mostly SOHCAHTOA stuff, so that is what we're going to spend most of the time on in this section. For the purposes of this section, we are assuming that you have a basic familiarity, a basic understanding of trigonometry, so we do move through a lot of this stuff rather quickly. We don't delve too deeply into trig. As most of you know, especially those of you who are juniors in pre-calculus or even sophomores in pre-calculus, you know that you can spend many weeks, if not months, on trig stuff, and we're going to do this in just a matter of a few pages. So again, nothing too deep here, mostly just going to do some review of some things that you already should know. The basic trigonometric functions and their ratios. So the basic trig functions are listed in this line here. I would go ahead and highlight at least the three on the left. I'm going to go highlight the entire line. The three on the left, sine, cosine, and tangent, and their abbreviations are in parentheses there, SIN, COS, TAN. The three on the left are the most common on this test. In fact, we have yet to see a question on any released SAT that is testing what are known as the reciprocal functions, which are these three over here on the right, cosecant, secant, and cotangent. That's not to say that College Board will never test the reciprocal functions, just that we've not seen many or any questions show up that have tested those functions. In this info box here, we are going to write down the ratios, the definitions of these 6 trig functions. And again, remember, the first 3, sine, cosine, and tangent, are going to be by far the most common. These next 3 down here, which are known as the reciprocal functions, will probably not show up, but we're going to give them to you just in case. So what do we have here? We have a triangle, a right triangle. There's a right angle down here at angle C. We have angle A, which has a measure of theta. Theta is just a Greek letter that usually represents an angle measure. It's just like an x or any other variable. So angle A has a measure of theta. We have our other acute angle up here, angle B. And we have to understand that if we are standing in, let's say we go into this triangle and we're standing in angle A where the theta measure is, and we're looking out across the triangle, we will see across from us or opposite us, we will see side BC. So side BC is the side opposite angle A or angle theta. And then right next to us, just to our right here, so we're looking out that way, we look to our right and we see the adjacent side, the side next to, that's what adjacent means, the side next to angle theta would be side AC. So again, this vertical leg of the right triangle is the side opposite of theta, and this horizontal leg or base of this right triangle is the side adjacent to theta. Some students do get a little bit confused because they see the hypotenuse also looks like it is adjacent to theta, but the hypotenuse is the hypotenuse, not the adjacent leg. These you could even write leg and leg here. So again, the opposite and the adjacent side, those are the names that we give to the legs, and then the hypotenuse, which is always the side across from the right angle in a right triangle. It's always the largest or longest side of a right triangle. The hypotenuse is over here. So again, we have an opposite side, an O, an adjacent side, an A, and always the hypotenuse opposite the 90-degree angle. Once we got all that down, we just need to talk about how we define these 6 trigonometric ratios, and they are defined as follows. The sine of angle theta is always going to be the length of the opposite side, the side opposite theta, to the length of the hypotenuse. So sine of an angle is the length of the side opposite that angle over the hypotenuse of the triangle. In our triangle up here, that ratio would be BC, which is the side opposite, BC, to the hypotenuse, which is AB. So BC over AB in our triangle would be the opposite side length over the hypotenuse length. That is how we would define sine of theta, opposite over hypotenuse. Cosine of theta is the length of the adjacent side over the length of the hypotenuse. So again, the ratio of the length of the adjacent side to the length of the hypotenuse is cosine of theta. In our triangle up here, since the adjacent side is AC, this ratio would be equal to AC over AB. Tangent is the opposite, the length of the opposite side over the length of the adjacent side. So tangent of an angle is defined as the ratio of the length of the opposite side, the side opposite that angle, again in our case that's BC, to the side adjacent to the angle, in our case that's AC. So those are the 3 major trigonometric ratios, the 3 very basic ones. You need to know all of those very well. I'm going to hop down here for a moment where we talk about this mnemonic or memory device. Almost all sophomores, juniors, and seniors will at one point have encountered SOHCAHTOA. And SOHCAHTOA reminds us that the sine of an angle is the ratio of the length of the opposite side to the length of the hypotenuse, and the cosine of an angle is equal to the length of the adjacent side to the length of the hypotenuse, and the tangent of an angle is equal to the ratio of the length of the opposite side to the length of the adjacent side. Again, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, that is SOHCAHTOA. Cosecant is the reciprocal function for sine. So instead of being opposite over hypotenuse, we reciprocate and we get hypotenuse over opposite. Secant of an angle is the hypotenuse over the adjacent. And again, that's just the reciprocal of the cosine function. And then the reciprocal of the tangent function is the cotangent function. So again, we just reciprocate these 2 sides. We get adjacent over opposite. We're not going to spend any more time than that on the reciprocal functions. You really just need to memorize them. If you want to come up with a mnemonic for those, you could, like CHO, SHA, CHO, SHA, cow. I don't know, that wouldn't work very well. Anyway, couple more points to keep in mind. We've already talked about the fact that the trig questions we have seen so far have not included any of the reciprocal functions. Doesn't mean that you will never see the reciprocal functions, just that as of now we have not seen them showing up. In terms of notation, you do need to understand that there are many, many ways to refer to a trig function and the angle that we are referencing. You could say something like the cosine of angle A. So in our triangle up here, the cosine of angle A would be the cosine of this angle, which would mean, again, the adjacent side over the hypotenuse, the cosine of angle A. But we could also refer to the cosine of angle A as the cosine of angle BAC. We could refer to it as the cosine of theta, since theta is the measure of that angle. Any of these notations, so again, cos A, or cos parentheses A, or cos parentheses BAC with the angle sign in front, cos of theta. These all mean exactly the same thing. What you need to understand is that whenever you encounter a trig function on this test, you are going to see the name of the trig function, whether it be sine, cosine, or tangent. Following the name of the trig function, you will see an angle that will be the relevant angle, the angle that we sort of need to stand in order to find our opposite side and our adjacent side. At the top of the next page, we are going to do a bunch of examples. These should be very basic. The vast majority of students who are sophomores, juniors, definitely seniors should be able to do these pretty quickly and confidently. I would try to work through these on your own before you watch me work through them, but if you are going to do them on your own, I suggest that you pay attention to this note over here and that you try to apply it. You always, when you're doing a trig question on this test, should be writing SOHCAHTOA, just so that you visually have that hint, that mnemonic in front of you, so that you don't make any careless mistakes and mess up some of the ratios. You also should be labeling sides AOH, adjacent, opposite, hypotenuse, depending upon what angle you are dealing with. As you see me work through these questions here and for the rest of this section, you will see me doing this stuff in general. So again, you might want to pause the video, work through this on your own. I am going to start right now. So first of all, I'm just going to write down SOHCAHTOA before I even start here. SOHCAHTOA. Always want to write that on basic right triangle trigonometry questions. We need to first of all determine sine of theta. So what do? I go to theta. I'm standing in angle theta. I'm looking out across, and what do I see? I see the opposite side, that 3 or CB side, that is the length of the opposite side, 3. My adjacent side, remember it's always the leg, never the hypotenuse. The adjacent side, I'm going to label that A, that's the 4. And then of course my hypotenuse, always across from the 90-degree angle, the 5 is the hypotenuse. So I have labeled, as I said over here, I have labeled A, O, H, all of the sides of the triangle. So sine of theta, remember we said that sine of theta, we define sine of theta as the length of the opposite over the length of the hypotenuse. I have so written down right here so I don't make any mistakes. OH, sine, O over H. So I'm simply going to take that 3 and I'm going to take that 5 and substitute them in for the length of the opposite, length of the hypotenuse, and I have the value of sine of theta for this triangle. Now for example 1b here, you notice we switched to the other angle. What I'm going to do to make this a little bit less messy and possibly less confusing, I'm going to draw the triangle again, A, B, C, and I'm going to use this triangle over here for when I need to evaluate trig functions of this angle x. Let me label this 90 degrees, because remember that when we jump from the theta over here on the left to the x over here on the right, our opposite and adjacent sides switch, because now when we look out across the triangle, we see this opposite side, which we know is 4 from the original triangle, and right next to us, this leg BC here, that is going to be the adjacent side. So again, my opposite and my adjacent switched because I have switched my acute angle. I'm no longer in this theta angle over here, and as always, the hypotenuse is across from the 90-degree angle, so my hypotenuse is still 5. So what do I do to find the cosine of the angle with measure x? I need adjacent over hypotenuse, so adjacent in the numerator, hypotenuse in the denominator. Adjacent is 3, hypotenuse is 5. So I got the same answer, 3 over 5. We're going to address that little quirk there about cases in which sine of one angle equals the cosine of another angle. We'll talk about that in another couple pages. Tangent of BAC. BAC is this angle here. So we're back to that theta angle. We're just calling it something different now. BAC, same angle though. So tangent of BAC, tangent is opposite over adjacent. So I need the opposite in the numerator, adjacent in the denominator. My opposite when I am in the theta or BAC angle is 3, and my adjacent is 4. 3 for opposite, 4 for adjacent, and I get 3 over 4. I really should be circling these. And then sine of angle B, where am I now? I'm no longer at theta, I'm in this x angle, so I'm going to use this triangle over here where I labeled my sides relative to the x angle. So what is sine of angle B? I got these wrong. That's not correct. This should have been C, and this should have been B. So we need sine of angle B, which is again back in that x angle there. The sine of angle B, as always, going to be opposite over hypotenuse. Opposite is 4, hypotenuse is 5, and 4/5 is the value of sine of angle B. Cosecant of CBA. Where's CBA? CBA, again, is this x angle. So I'm going to use this triangle where my sides are labeled according to the x angle. CBA is that x angle. So the cosecant, remember that cosecant is the reciprocal of the sine function. Sine is opposite over hypotenuse, so the reciprocal would be hypotenuse over opposite. Okay, so cosecant is 1 over the sine of an angle, in this case angle CBA, and 1 over sine would be 1 over O over H, and that would be 1 times, I'm just multiplying by the reciprocal of that denominator, 1 times H over O, which gives me H over O, just showing you another way to think about reciprocating the sine function there. Again, hypotenuse over opposite, so that is a 5 over a 4. 5 over 4 is the value of the cosecant of angle CBA. So again, just a few basic examples to demonstrate to you how we use the definitions to determine the ratios of some side lengths in a right triangle. Moving along, trig without triangles. Often you will see trigonometry questions, but no triangle will be given. Obviously, on the previous example, we were given a triangle, but occasionally we will not be given a triangle, and we will often want to simply draw a triangle based on the description in the question. So let's go ahead and highlight draw the triangle. In order to do a lot of these questions, we do need to know the Pythagorean theorem. The Pythagorean theorem is given at the beginning of both math sections, but you should have it memorized. A squared plus B squared equals C squared. Remember that in the Pythagorean theorem, A and B are the legs or perpendicular or shorter sides of the right triangle, and C is the hypotenuse. Always, 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 A and B are the legs and C is the hypotenuse. So A squared plus B squared, the squares of the two legs added together must equal the square of the hypotenuse. Those are side lengths, obviously. The square of the side length of one leg, square of the side length of another leg, and the square of the length of the hypotenuse. The most common Pythagorean integer triples that you will encounter on the test. By the way, the Pythagorean integer triples just means 3 integers that fit into the Pythagorean theorem. They would be the 3, 4, 5, the 5, 12, 13, and the 7, 24, 25. And again, if you were to do, let's do this here. 7 squared plus 24 squared, what do we get? We get 625, and indeed, if we square 25, we get 625. So we just found that 7 squared plus 24 squared is going to equal 25 squared. So 7, 24, 25 are 3 integers, nice neat integers that fit into the Pythagorean theorem. You do need to understand that all of the multiples of these triples, let's write down and their multiples. All of the multiples of these triples will also fit into the Pythagorean theorem. So the 6, 8, 10, or the 10, 24, 26, just multiplying those first 2 triples by 2. Let's take a look at an example on which we are not given a triangle, and therefore we will want to or need to construct a triangle using the information in the question. If you are comfortable with trig, confident with trig, you may want to do this question on your own. Pause the video and do so. In example 2, we are told that triangle PQR has a right angle Q. We are told that the sine of angle R is 3 over 5, and what do we need? We need the tangent of angle P. So again, what are we going to do? We're going to draw a representative right triangle. So let's draw a right triangle. They tell us that the right angle is Q, so I'm going to label that vertex with the right angle in it. I'm going to label that Q. We know that we have a R, and we know that we have a P as well. I'm just going to randomly place the R and the P in the remaining two vertices. They do tell us that the sine of R, this is the next phrase here, the sine of R is 3 over 5. So remember what I want to do. I'm going to write SOHCAHTOA, which I should always do on trig questions. R is the relevant angle, so I am going to label the sides relative to angle R. The opposite side would be this PQ. The adjacent side would be this leg RQ, and the hypotenuse always across from the 90. So now I have my sides labeled, and now I'm going to use the given trigonometric ratio. I know that sine is opposite over hypotenuse, so this is opposite. This is hypotenuse. So that means this guy over here is going to be 3, and this guy over here is going to be 5. That's the hypotenuse. That means, if I know my Pythagorean integer triples, that means the A must be 4. A 3, 4, 5. One thing you should be careful of, I'm going to write this note over here. If you ever see College Board giving you a right triangle in which, let's say you have a 4 and you have a 3. So you have a 4 on the hypotenuse and a 3 on one leg. Some students make the mistake of thinking the remaining side must be 5 because 3, 4, 5. But remember, in the 3, 4, 5 triangle, as in all right triangles, the biggest value, the 5, must be on the hypotenuse. It must be the C side or the hypotenuse side. You cannot have a right triangle in which you have a leg being greater than, having a greater length than the hypotenuse. This would not be possible. There's no way this leg could be 5 if the hypotenuse were 4. What you would do in a situation like this is you would need to do Pythagorean Theorem. You would do 3 squared plus the unknown side squared, we could say b squared there too, equals the 4 squared, 16 minus the 9, and so on and so forth. That is how you would determine the length of the remaining side. So just a note of caution there. Back to example 2. So again, we now know that our 3 sides of this triangle are 3, 4, 5, one of the Pythagorean triples. They're now asking us for tangent of P. So what we're going to do is I'm going to erase this A and this O, because now, relative to angle P, this is actually the opposite side and this is the adjacent side. Tangent requires us to find the ratio of opposite to adjacent. Opposite is 4, adjacent is 3, so tangent of P should be 4/3, and we are done. Example 2. Moving along to the next page, here we need to talk about the fact that trigonometry will occasionally involve similar triangles and proportions. A lot of students get into the habit of thinking that when you see something like sine of r equals 3 over 5, that you must have a side length of 3 in your triangle and a side length of 5 in your triangle, and that is not true. 3 over 5 is a ratio. It is a reduced or simplified ratio. We could just as easily, if we are looking for the sine of r, and we see that the sine of r is 3 over 5, we may be dealing with a triangle in which the opposite side, right, that 3 is opposite, that 5 is hypotenuse, so SOHCAHTOA. The opposite side could be 6 and the hypotenuse could be 10. And in that way, the sine of angle r would be opposite over hypotenuse, which would reduce to 3 over 5. It could even be the case that this opposite side is 0.15 and the hypotenuse is 0.25. The 3 and the 5 represent a simplified or reduced relationship. We do not necessarily know if we are dealing with a triangle that has side lengths of 3 over 5. How do we figure it out? We've got to look at the other information that's given in the question. Example 3, you may want to pause. If you are confident with this stuff, pause, do example 3 on your own, and then watch me work through it. In example 3, we have a right triangle ABC. They tell us that BC equals 6. We can see that up here. Sine of angle X, sine of this angle is 1 over 2. and they want the length of AB. The length of AB. Let me get rid of that. The length of AB. Okay, so right off the bat, let's write down SOHCAHTOA. And they're talking about the sine of this angle here. Let's label our sides. This would be the opposite side, the side opposite x. This would be the adjacent side, and the 6, as always, would be the hypotenuse. So that 1 is the opposite, and that 2 is the hypotenuse. But if we look at the hypotenuse, we don't have a 2 here. We have a 6. Some students will get confused by that. They'll say, why is there a 6 over there when there's supposed to be a 2? Remember that this 1/2 is a reduced or simplified relationship. What do? We set up a proportion. We know that the ratio of the opposite to the hypotenuse must be 1 to 2. This is the reduced relationship, and we will set that equal to the actual relationship, which is something over 6. I actually shouldn't be using an x there. I should be using, we already have an x as the measure of the angle. So what do I want to use there? I want to use, let's just use AC. That is the opposite side, AC. So I'm putting AC, the opposite side, in the numerator there. So now I have this nice proportion. I cross multiply. I get that 2AC equals 6. I divide by 2, divide by 2. And I now know that AC must equal 3. That is the length of the opposite side. What are they asking? They're asking for the length of AB. What do? I can do Pythagorean Theorem. There is another way to do this. I'll talk about it in a moment, but I'm going to do Pythagorean Theorem. I know that 3 squared plus AB squared must equal BC, or the hypotenuse squared, which is 6 squared. I have a 9 plus AB squared equals, 36. I subtract the 9. I get AB squared equals 27. I square root. I get that AB equals, I'm going to break this root 27 down as follows. I'm going to do root 9 times root 3, which equals 3 root 3. Is that what they are asking? What AB is? Yes, it is 3 root 3. So that's how I would use proportions, similarity, to take an actual side length and relate that actual side length to a reduced ratio. Now, over here, there is this little note that you could have solved this question in another way. If you're very familiar with trig and you've seen sine of x equaling 1/2, you would have known that this is a 30, 60, 90 triangle. Some students might have picked up on that, and that's perfectly fine. If you want to do the question using your 30, 60, 90 rules, perfectly fine. You can do the question that way. We went through it in a slightly different way so that we could demonstrate that trig questions will often involve proportions. On example 4, again, may want to pause the video and try this on your own before you see me work through it. What do we have here? We have a triangle RST with right angle S, hypotenuse of 26. They tell us that cosine of R is 12 over 13, and in this case they want the area of the triangle. I am going to once again draw a representative triangle here. I'm going to draw triangle RST. They tell us that the right angle is angle S. I will randomly put an R here and a T here. So triangle RST with right angle S. They do tell me that cosine of R, that's this angle here, is 12 over 13, which means that the ratio of, actually, let's write SOHCAHTOA, and let's label our sides. This would be opposite, this would be adjacent, this would be hypotenuse. So the ratio of this side down here, RS, the adjacent side, to the hypotenuse must be 13. They tell us that the hypotenuse is 26. So we do not have a 13, we have a 26. Again, multiple ways you can go from here. You can see that there's just a times 2 relationship between the ratio numbers here and the actual numbers. I'm going to go ahead and set up a proportion. That's the maybe more conventional, possibly safer way to go. So in my ratio or reduced relationship, I have a 12 in the numerator where the adjacent side is, a 13 in the denominator where the hypotenuse is. In my real triangle, my actual values, I have a 26 down here, and I have RS. RS is the adjacent side. I'm going to, in this case, I am actually just going to see that times 2 relationship. Why? It's a no calculator question. I don't want to have to multiply 26 times 12 I can do it, obviously, we could do it, but I don't want to have to. So I just want to see that I'm multiplying by 2 across those denominators, which means I need to multiply the numerators by 2, and I will get that RS equals 24. That is 12 times 2. So I now know that this side is 24, and I should be aware that this is a multiple of the 5, 12, 13, the 5, 12, 13. A multiple of the 5, 12, 13, I would get 24 here and 26, which I already know I have, 24 and 26, which means the shortest side must be a 10. That's the opposite side, the remaining side. So now I need the area of this triangle. I have the base, I have the height. By the way, the area of a triangle, this formula is given to you on the test at the beginning of the math sections, 1/2 the base times the height. So in our case, we have area equals 1/2 base, which is 24, times the height, which is 10. And easiest way to do this, probably just to multiply the 24 by 1/2, get 12. 12 times 10 is 120, so my area should be 120 square units or square centimeters. That is how we use similarity and proportions on some trigonometry questions. We have to talk very briefly about cofunctions and what cofunctions mean and a particular relationship between cofunctions. I'm going to draw your attention to examples 1a and b on the previous page. You notice that when we did the sine of theta, which was one of the acute triangles, one of the acute angles in this right triangle, and then when we did cosine of x, which was the other acute angle in this right triangle, we got the same value. And that was because, it's illustrated up here, it's because when we do the sine of theta, the opposite side is 3, and the hypotenuse is 5. And when we do the cosine of x, that 3 is now the adjacent side. So the opposite side of theta is the same as the adjacent side of x, which is why we're ending up, and obviously the hypotenuses are always the same. That's why we're ending up with the same values there. So it is always true that when you do the sine of one acute angle and then you do the cosine of the other acute angle in a right triangle, those two values will be equal. So when x and theta add to 90 degrees, you will always have this relationship where the value of one function will be equal to the value of its cofunction of the complementary angle. Let's go ahead and write this down here and see a couple more examples so that we can get a really good picture of what's going on here. So first of all, let's go ahead and highlight this. The cofunctions of complementary angles are equal. So we have sine, and we have its cofunction, cosine. We have tangent, and we have its cofunction, cotangent, although again, you probably won't see that. We have secant and cosecant. Probably won't see those either. The most important ones here will be the relationship between these two, the sine and its cofunction, cosine. If you have complementary angles, angles that sum to 90 degrees, then it will always be the case that the sine of one of those angles will equal the cosine of the other angle, and vice versa. You also can express this relationship as sine of an angle equals cosine of 90 minus that angle. Same thing with angle B. You could express this with angle B as well. Let's do a couple more examples here so that we can further illustrate this point and hammer it home. In example 5, we have triangle ABC having right angle C. We have cosine of A equaling 7/25, and we need the value of sine of B. That's what they are asking here. So if you are really confident with this whole idea of cofunctions of complementary angles, you can be done this question in 2 seconds. And that's great. If you feel that way, you can answer this right off the bat. Go ahead and answer it. I am going to work through this just so we can see what's going on here. So we have triangle ABC. The right angle is angle C. We have an A and we have a B. Again, just labeling those other angles randomly. It doesn't really matter where I put the A and the B. That's the first phrase. I am going to go ahead and write down so ka toa. They then tell me that cosine of angle A, there's my relevant angle, at least for now. So cosine of angle A, I'm going to label this side adjacent, this side opposite, and this side hypotenuse. The cosine of angle A, they tell me, is 7 over 25. So that means that the adjacent over the hypotenuse, adjacent over hypotenuse, is going to be 7 over 25. So I'm going to label those two sides 7 and 25. And if I know my Pythagorean integer triples, I do know that this side is going to be 24, the other leg. However, that other side is going to become slightly irrelevant because they are asking me what the sine of angle B is, sine of the other acute angle. Well, remember that angle A and angle B, those are complementary angles. They must sum to 90 degrees. We have 90 degrees here. The remaining 90 degrees must be made up between the measures of these two other angles in the triangle. So the sine of angle B, let's go ahead and relabel these sides. We want to label this one the opposite. That's the opposite side. Sine of B is going to be opposite over hypotenuse. So here's the opposite side. Hypotenuse is still 25, and therefore the sine of angle B, this would be the adjacent side to B, the sine of angle B would be 7 over 25. 7 over 25, which you notice is exactly the same as what the cosine of A was, because the cosine of A must equal the sine of B when A and B add to 90 degrees, which we can see in this triangle they do. So if we knew that the cosine of angle A was 7 over 25, we would know that the sine of B, which is what the question is asking us for, must also be 7 over 25. So again, can you do this question drawing the right triangle as we've done on the previous few examples? Yes, it would be perfectly fine. Will you save yourself a little bit of time to understand the relationship between cofunctions and cofunctions of complementary angles? Yes, you will. In example 6, again, might want to pause the video and try this question on your own. In example 6, you notice that the question just comes right out and tells us that the sine of one angle equals the cosine of the other. Could I draw a triangle here and try to work some of this stuff out, maybe throw in some numbers for my side lengths and such? Yes, I could, but there's really no need to, because once again, if we know the rule about the cofunctions of complementary angles, we know that it is always the case when the sine of one angle equals the cosine of another angle, then what must be going on is that x plus y must equal 90. X and y must be complementary. They are asking us for x plus y, which means we're done. We know that x plus y must equal 90 because the cofunctions of complementary angles are always equal. If the sine of x is equal to the cosine of y, that means x and y must be complementary angles. At the top of the next page, we talk about trig on the xy plane. So, as of this point, we have talked pretty much exclusively about how trigonometry works in the acute angles of a right triangle. Trig on the xy plane allows us to expand our definition of trigonometry past the acute angles of a right triangle. Trig on the xy plane allows us to talk about pretty much any size angle and what the trig functions of those angles would equal. We are going to introduce this with this little info box here. I'm going to make this a little bit bigger. So here's what we have in this figure. We have a circle, this gray circle. We have the circle centered at the origin at 0, 0. We have the circle with a radius of r. There's our radius. We are then going to, I'm going to clean this up as I go so that I don't get this too messy. We are then going to create a central angle theta. Theta is right here. We create a central angle theta. How do we create that angle? We use the positive x-axis as one of the angle's rays, and then we have this terminal ray over here that we have rotated a bit in the counterclockwise direction, and between those two rays, again, we have an angle theta. So again, we've got this circle centered at the origin, it's got a radius of r, and now what we have done is we've created a central angle in this circle by rotating a ray away from the positive x-axis and landing at some point here in the first quadrant. Then what we are going to do is we're going to make a little right triangle. And the way that we're going to do that is we're going to drop a little altitude, a little vertical segment from the point at which the terminal ray hits the circle down to the x-axis. And then we are going to complete the triangle by drawing a horizontal segment from the origin out to where the vertical segment hits the x-axis. And again, now you can see that we have a right triangle. And in that right triangle, the hypotenuse is r, the radius of the circle. And we actually know that the lengths of the legs are going to be x and y because we have called the point at which the terminal ray hits the circle, we've called that point xy. And when we have this point xy, we know that the distance to the right must be this x coordinate, and the distance up must be this y coordinate. That is true of all points on the xy plane. If I have, let's say, this point over here, to get to that point, I would go right an x value and up a y value, and that point would be x comma y. So again, I have a right triangle now with legs of length x and y, horizontal x, vertical y, and a hypotenuse of length r. And now I can actually figure out what the trig functions of this angle theta are, of this central angle theta. The cosine of theta, let me write down, SOHCAHTOA. The cosine of that angle is going to be the adjacent side. Oops, that is supposed to be an h. The adjacent side, which is x, over the hypotenuse, which is r. So in this triangle, the cosine of that central angle theta is going to be x over r. The sine of this central angle theta is going to be opposite, which is y, over the hypotenuse, which is again r. And the tangent of that central angle theta is going to be the opposite, y, over the adjacent x, y over x. So in this triangle, I now have my ratios, my basic trig ratios. In terms of how this, by this point, you might be wondering how this is any different from what we've already learned, and the answer is it's not all that different. It will become slightly different in a moment, but example 7, most of you should be able to handle this example by this point, so I would pause the video and try it on your own. So in example 7, we are told that point A is there, lies on ray OP. I see ray OP there, great. If the coordinates of A are 6, 3, what is the cosine of theta? Okay, so the coordinates of point A are 6, 3. What does that mean? That means that this distance here and this distance here are known. They are a 6 and they are a 3. We want the cosine of angle theta. Let's write down SOHCAHTOA, as we always do. SOHCAHTOA. The angle, the relevant angle is theta. The 6 is our adjacent side. The 3 is our opposite side. And then we have our hypotenuse. In order to find cosine of theta, we do need the adjacent side, which we have. We do need the hypotenuse, adjacent hypotenuse. We do need the hypotenuse, which we don't have. The hypotenuse is OA. How do we figure out OA? We do Pythagorean theorem. We're going to do 6 squared plus 3 squared equals OA squared. This is 36. This is 9. This is 45 equals OA squared. I'm going to break the 45 down into root 9 and root 5. Square root. I skipped that. Going too fast. So that means that OA is going to equal 3 root 5. OA is 3 root 5, and I now have my hypotenuse. My OA is 3 root 5, so this is 6 over 3 root 5. That will reduce to 2 over root 5. I could rationalize that denominator, but I am not going to. If it becomes necessary on the test to do something like that, I will. Just so you know how you would rationalize that denominator, you would multiply both numerator and denominator by root 5, and you would get 2 root 5 over 5. Either of those answers would be acceptable. So again, in example 7, in the info box up here, you might be looking at this thinking this is not much different from what we've already done. And again, you're totally right. We've not done anything vastly different yet. But we are going to do something very different when we start to make that terminal ray land in different quadrants. Remember, that terminal ray does not have to land in the first quadrant. It could land in the second quadrant, the third, the fourth quadrant. But anywhere the terminal ray lands, we can still construct that triangle and determine the values of our trigonometric functions based on the points or the coordinates that we're dealing with. We can see an illustration of this at the top of the next page. So at the top of the next page here, you can see this figure on the left. We have the terminal ray landing in the second quadrant, but again, we can construct that triangle, and we use this reference angle here, which is basically the acute angle that the terminal ray makes with the x-axis. We can use that acute angle to evaluate our trig functions. So, you know, the cosine of this theta, we would use this reference angle, and we would say that the adjacent side is this x, the hypotenuse is still that r, so we would have cosine of theta equaling x over r. Here's the catch though. Because now we are dealing with the xy plane and we're dealing with quadrants, we do have to worry about our signs, these signs of these x and y coordinates. For instance, in this second quadrant, all of our x coordinates are actually negative and all of our y coordinates are positive. So this value in the numerator here, this value is going to be negative. The radius we always call positive. Radius never gets negative. So the cosine of theta in quadrant 2 is actually going to be negative. We're going to see an example or two of this in a moment, so don't worry about that too much right now, but you do have to understand that as that terminal ray rotates around the center into quadrant 2, into quadrant 3, into quadrant 4, back into quadrant 1, we are going to have to account for the signs of x and y when we are calculating the values of our trig functions. The main thing that you need to understand right now is, again, we can make our terminal ray land in any quadrant, construct the triangle, and then find the values of the trig functions, the trig ratios, using the reference angles, which are the acute angles that the terminal ray makes with the x-axis. Signs of the points on the xy plane. I said a moment ago that the signs of the points on the xy plane will become relevant when we are doing trig on the xy plane, so let's run through these right now. You might want to pause the video and do this on your own. What I am looking for here is the signs of the coordinates in each quadrant. So the x coordinate in quadrant 1, always going to be positive, y coordinate positive. In quadrant 2, x coordinate negative, y coordinate positive. In quadrant 3, both coordinates negative, x and y. In quadrant 4, we have positive x's and negative y's. Very important that you have that memorized. Most of you should already have it memorized. Down at the bottom on example 8, again, if you're feeling confident with this stuff, if you know your unit circle trigonometry really well, you probably can do example 8 on your own. If so, pause the video, try it out. I'm going to work through it right now. They tell us here that we have this figure, we have a circle centered at 0, 0, we have a radius of 5, all that's sort of labeled and drawn in this figure. Graphed on the xy plane, we need the sine, cosine, and tangent of theta. So first of all, let's write down SOHCAHTOA. Remember that what we do here is we construct a triangle. So I'm going to draw a vertical segment here, a horizontal segment here, and remember that our reference angle is this angle in here, the acute angle that the terminal ray makes with the x-axis. So that's my reference angle, and I am going to call this side this will be the adjacent side, this will be the opposite side, and this will be the hypotenuse. And we also know, because of this coordinate right here, that this length here is an x value. We do have to always keep in mind that we're dealing with this sine pattern in quadrant 2, so we'll keep that in mind. And then this vertical segment, this vertical leg of my right triangle must equal 3, because that is the y coordinate at this point. So that point is 3 units above the x-axis. So I now know that I have a 3 on one side, a hypotenuse of 5. I should recognize this is one of my opportunities to use a 3, 4, 5. I know the 3, I know the 5. This last side must be 4. However, the x the x value there should be, I'm not going to cross that off, I'm just going to write to the left of it, negative 4 comma 3. So this x value here is actually a negative 4. So now in evaluating my trig functions, I do have to account for the fact that my adjacent side is negative 4, my opposite side is 3, my hypotenuse is 5. So this should be very quick now. Sine of theta, remember sine of theta is my opposite over my hypotenuse. Opposite is positive 3, hypotenuse, the radius is always positive, so my sine of theta is 3/5. My cosine of theta is going to be the adjacent over the hypotenuse. Remember we said the adjacent here is not positive 4 but negative 4 because I have to account for the quadrant that I'm in. So negative 4 over the hypotenuse, which is 5. Negative 4/5 is the value of my cosine of theta, and then the value of tangent of theta is going to be opposite over adjacent. Opposite is 3. And the adjacent is negative 4, so my tangent there is also negative. It is negative 3/4. And that is how you do example 8. It might be worth noting that because your cosine is associated with your x values, right? The x values will always be the adjacent side. So cosine is associated with your x values, sine is associated with your y values. Tangent is actually associated with both x and y because of the fact that the opposite and the adjacent are relevant to the tangent function, so x and y. So that actually means you will know that whenever you are in a quadrant where x is positive, you are also in a quadrant where cosine is positive, where x is negative, cosine is negative. So you could even go back up to this figure up here, and you could write this and then in terms of tangent, remember that tangent will be positive in this quadrant because both x and y are positive. Tangent will be negative in this quadrant because you will have one negative and one positive. The adjacent will be negative and the opposite will be positive. So a negative over a positive will give you a negative. A negative over a negative will give you a positive, and then a positive over a negative over a positive will give you a negative. Some students have learned a quirky little mnemonic for this. All students take calculus. If you know that mnemonic and it helps you, go ahead and use it. I don't particularly like that mnemonic because I like to simply know that my cosine is associated with my x values and my sine is associated with my y values and my tangent is associated with both of those values. Anyway, moving on to the final example here, and what is probably the most difficult example. If you feel confident, you can try this one on your own. If not, you can just watch me work through it. So in example 9, again, we have this circle on the xy plane centered at the origin. We are not given the radius here. That is not true. We are given the radius. We know that the radius is 1. They tell us that this point is 1. They tell 1, 0. They tell us that this point is 0, 1. So we know the radius of this circle is 1. We know this length is 1. And then what are we told? We are told that cosine of theta equals 1 over 3. We want the coordinates of point A. So I'm going to write SOHCAHTOA. I am going to construct my right triangle. How do I do that? Let me move this one over here so it doesn't get in the way. I'm going to draw my vertical segment and my horizontal segment. Remember that my relevant angle here, my reference angle here, is this acute angle that the terminal ray makes with the x-axis. This would be the opposite side, which again is the y coordinate of point A. This is the adjacent side, which again is the x coordinate of point A. And what I know here is I know that my cosine of theta, my cosine of this reference angle, is going to be 1 over 3. And I'm going to set up a proportion here. Some of you might not need the might not feel the need to set up this proportion, but I'm going to set it up because I want to do this again in the most conventional way possible, just so everybody knows what the heck I'm doing here. So my ratio of adjacent to hypotenuse has to be 1 to 3, but the real length of the hypotenuse is 1. and my adjacent side is my x. So that means that 1 over 3 equals x over 1, which means that x equals 1/3. I can cross multiply and get 3x equals 1, divide by 3. So that means my x value here is 1/3. Is that a positive x value? Yes, it is, because I am in the fourth quadrant and my x values there are positive. Now I need to determine my y value because I need the coordinates of point A. So what am I going to do? I'm going to do Pythagorean Theorem. I am going to do 1/3 squared plus my y value squared has to equal 1 squared. 1/3 squared is 1/9. So I'm going to subtract the 1/9 from both sides, and I'm going to get y squared equals 1 squared is 1 minus 1/9 is 8/9. To get my y value, I square root, and I get y equals, I should technically write positive negative there. It's going to equal root 8 over root 9. So that is root 9 is just 3, and then root 8 is 2 root 2. So I have plus or minus 2 root 2, but remember I'm in my fourth quadrant here, which means I have that positive negative scheme, which means the positive value here is irrelevant. I know I need the negative value. The y coordinate there is going to be negative 2 root 2 over 3, which means the coordinates of point A are 1/3, that was my x value, comma, negative 2 root 2 over 3. Those are the coordinates of point A, and I am done. Again, I understand that last example is a little bit more involved, a little bit more difficult. I will say that's probably the hardest type of trig question that you will see on this test. So if you were comfortable with it, you're gonna be fine with the trig on this test. If you were not, I would review it. I would ask your tutor about it. You will see 1 or 2 questions in the homework that look like this question, so you'll get a little bit more practice at doing stuff like this. That is it for trig. Not all that big of a body of knowledge to know for the trig on this test, fortunately. Make sure you review this information often, especially before you do the homework questions.